Is Martin Schweitzer. Martin's a software developer, tech lead, and is a manager at the Bureau of Meteorology. He has a passion for solving complex problems, and one of those, I think, is fuzzy string search. So Martin's going to talk about finding Currajong, fuzzy string searches in Python. Thank you, Martin.
Thanks, Andrew. Okay, earlier we had a few technical issues, so hopefully they will be solved by now. There we go. It should come up now. Just, yeah. Good. And we rely on some internet bandwidth, so let's cross fingers. Okay, so good software generally starts with a good user story. And so we're going to start this with a little mystery. So I'm sitting out there, the sun is setting, it's a nice red sunset, and my mobile phone rings. It's my partner, who happens to be in West Australia prospecting. And she says, help, help, I've been kidnapped. I'm near Currajong, and I'm in the boot of a red car. Okay, well, time is of the essence. So first thing I do is go to the Gazetteer of Australia, because that's got, what's it got, 370,000 place names. And I quickly type in Currajong and hit enter. This is where we hope we've got some internet connectivity. And it's not the fastest search engine in the world, so. And we see there's a whole lot of Currajongs there, but none of them are in West Australia. Okay, well, what's the next thing we do? We Google it. So go to Google, type in Currajong. Yep. Currajong School, not particularly helpful. Let's see. Anyway, Google's not much help there. So I do what any software developer would do. I write my own app. So I've called it Gazetteer, and it's sort of Martin's Gazetteer. Download all the data from the Gazetteer. And I type in Currajong. Takes a few seconds. Fortunately, I don't have that little wait thing. I think, search, sorry. Yeah, we got it. Okay, there's a whole lot of Currajongs with a C, but I see there is a spot in WA, and it's called Currajong with a K. So what the rest of this talk is, how do we do the kind of match where we've got names and they're not always correct? Somebody types Currajong with a K instead of a C, or a C instead of a K, etc. So let's have a look how we do it. Okay. So this is what you can download the data from the Gazetteer. It's open data, government data. And as they mentioned earlier, it's about 370,000 place names. But if you look at something like Williamstown, there's Williamstown Rock, Williamstown Beach, Williamstown Golf Course, Williamstown Secondary School, and so on. So what I did was clean that data a bit and looked for only the places that were like place names. So I got a file of about 80,000 place names as CSV. So all the examples we look at, we'll be trawling through this file of 80,000 names and looking for, in this case, Currajong. And what we'll hope to see is Currajong with a K plus maybe some other forms. So the first technique that we use is one that a lot of people know about, called Hamming distance. And quite simply, if you've got two words, you put them one on top of the other. The Hamming distance is the number of differences between those two words as we compare them letter by letter. So Currajong and Currajong, they're identical, so the Hamming distance is 0. If I spell it with a K, only the K is different. So the Hamming distance there is 1. If I spelled Currajong with 1 R instead of 2, we run into, I've got Currajong and Garrywong, and there we see quite clearly the Hamming distance is 4. The C is a G, the U is an A, the A is a Y, and the J is a W. So, and finally, if we leave out the R from Currajong, suddenly we've got a distance of 6 because everything has shifted left one letter. So from that point on. However, this can still be useful. So it's very easy to implement, which is an advantage of this algorithm. What I've done there is just zip the two words together and then counted the number of differences using a list comprehension and return that. And in this particular piece of code, I've said, if the distance between the words is less than 3, in other words, 0, 1, or 2, let's print that line of text. So we run that using the word Currajong over the GA data, and we get 185 results. And we get things like Barajong, Kara, Karamanga, Currarong, Currawong, etc. And there's also quite a bit of noise. One of the things about this algorithm is it's only defined if the two words are the same length. So where we've got two words, one is longer than the other, we only compare up to the length of the shorter word. However, let's go to words where the Hamming distance is either 0 or 1. And we see, obviously, we get fewer results because it's a subset of the first set. And we get Currarong, Currawong, and we see we get the Currajong with a K, which is great. But we also get places like Murra and Q, C-U-E. So it looks like an improvement, but there's also noise. We're getting some false positives, as it were. So we can improve this once again. And what I've done here is I've taken the Hamming distance, but that very last line, I've said if the word that we gave it, like Q, is shorter than the word we were looking for, add a penalty. I see people, these slides will be available after the talk, so if you want, you can take photos, but you don't have to. So we've added a penalty at the end for words where their name is shorter than what we've typed in. We don't add a penalty if it's longer because we want to pick up things like Currajong North. When we run this improved Hamming, we get Barajong, Karamanga, Currarong, etc. We get the Currajong that we're looking for, which is important. And we see we don't get all those false positives like Q. So this is a pretty good result. We've got 37, which is a nice size of a result set. OK, nice, simple algorithm. It's got some nice properties. Can we do better? So the next thing I tried is a really old algorithm called SoundX. I'm rushing ahead of myself. In this case, we've looked for where we've got a distance less than 2, in other words, 0, 1 differences. And in fact, this is even better. We get 21. We get the WA Currajong. And most of these results look pretty much like Currajong. So in fact, this is almost our benchmark for the moment. OK. So next algorithm we look at is called SoundX. And this was actually developed in the 1920s, in fact, before computers. And what they did is they said, take the first letter of the word, so in Currajong it would be C, and then for the next 3 positions, then remove any vowels that you have. And then if you've got a B, F, P, or V, replace it with a 1. If you've got C, G, J, etc., replace it with a 2. And R is 6, etc. So Currajong, we would have the C, and then it would be, I think, 627, 625. And so what we can do is we can index every word in our gazetteer, and we can say, OK, if it's equal to 625, well, according to this algorithm, it sounds like Currajong. So the next algorithm's a bit more complex after this, and so I looked for a library that would have that algorithm, so I wouldn't have to write it by hand. I found this library called Jellyfish. Fantastic library. It's efficient. It does exactly what you want. We'll see it in a second. And it also had the SoundX, so I decided to use the Jellyfish SoundX. So here's my program. We import Jellyfish. Go through the gazetteer line by line. We split those fields, and if the SoundX is the same as that value, that signature we got for Currajong, we print that line. So the code is fairly straightforward. Unfortunately, the results aren't great. So according to Soundex, all these words sound similar. Corrigan, Corrigan's Camp, Coursing Park, Crackneck Point Lookout. So I think the advantage with Soundex is almost every database has an implementation. Oracle does, SQLite, Postgres, and that comes packed with it. The disadvantage is it's not particularly useful. One sort of advantage, if it was even slightly useful, is that you can pre-index your list, which of course we can't do with Hamming distance. But once again, it's not useful. So somebody came up with, I guess, what could be thought of as an improvement to Soundex called Metaphone. Metaphone says, OK, drop duplicate adjacent letters except for C. If the word begins with K, N, G, N, P, N, etc., drop the first letter because things like night and nu, etc., the first letter is silent. Drop B if after M at the end of the word, so like comb, it would drop the B. And it goes through 17 rules like that and comes up with a number or a transform that, once again, the idea is that similar words should have a similar metaphone. And as I mentioned, Jellyfish has a metaphone function. And so, in fact, all we've changed in this code is which function we're calling. Before we called Soundex, now we're calling Metaphone. And so let's have a look how Metaphone does. It doesn't do too badly. It brings up Currajong in WA. It also brings up Currajong and Currajong, which sound similar enough. One of the things you'll notice is that in that list, it only picked up 10 results. Other algorithms gave us far more results. One of the problems, which I've shown you, is that if we look for Melbourne, it gives us Melbourne, spelled how we'd expect, and Melbourne. But if we grepped Melbourne in the gazetteer, we find that there's things like Melbourne, but there's also Melbourne North and Melbourne South, which it didn't pick up because of the way the algorithm works. So we can improve on Metaphone by saying, OK, well, if the person has given you a word 8 letters long, cut off the first 8 letters of the word in the gazetteer and compare that. So that would work. And so I did that. And so we get our improved Metaphone, which has 14 results. And they look quite good. They all sound like Currajong. We didn't get the Currawong or the Curragong, but they're reasonable. OK, so where do we go from here? Well, we go back to the Hamming distance, and we look at another algorithm called Levenstein distance. So you'll remember with Hamming distance, one of the problems was if a letter had been removed, suddenly everything was out of whack. And so with that Currajong C and K, in the top one, I've left out the second R, so we get distance of 7. With Levenstein, what it says is we will treat insertions, deletions, or substitutions as one, let's say, penalty point. And so we can see that the C becoming a K is a cost of 1, and the R being deleted is a cost of 1. So this algorithm, Levenstein, would return 2 when comparing those two words. Once again, Jellyfish happens to have a Levenstein distance, which was really useful. So once again, the code was really easy. And all we have to say is, in this case, if we've got a distance of less than 2, in other words, if there's 0, 1, insertions, deletions, or substitutions. We print this. We get 28 results. And we notice this will pick up things like Baragong, which Metaphone didn't. And it also picked up Currajong. This was with a distance of 2, so 0, 1, or 2. 28 results. I reduced it to say, OK, only consider those with a distance of 0, 1. And that gave us 15 results. and my acid test in each of these is, does it pick up Currajong in Western Australia, which clearly this one does. It's also worth noting at the bottom that 0.1 seconds. So most of the algorithms we've looked at so far have been between 0.1 and 0.3 to read a file of 80,000 lines, parse the CSV, and do whatever test. So what was the algorithm I used when I did my initial Mazetier? Well, it's after doing a lot of reading and looking at algorithms, I discovered that the Python library comes with an algorithm that returns differences between words. And it's in a library called difflib. And the function is difflib.sequencematcher, and you give it 2 words. And it returns a ratio. If the ratio, I think, is 1, it means the words are equal. The less equal the words are, the lower the ratio goes. So this was my initial results. It came up with 772 results. So I just sort them by rank, the highest ratio first, et cetera, and take first 20. But problem here is looking at the timing, it took more than 10 times as long as any of the other algorithms, or roughly 10 times as long, which I wasn't particularly happy with, which explained why my first thing was so slow. So I decided to use Levenstein, but then I decided to improve it slightly. And one of the good things about Levenstein that you don't get with things like Metaphone or Soundex, it tells you, gives you a result of either 0, 1, 2, etc. And I thought, okay, if they type in Currajong, and there's Currajong North, I'm comparing only Currajong with Currajong, so I'm getting 0. But because the word in the gazetteer is longer, I'll add a penalty of 0.5. If it came up with one difference, like Currajong with a C and a Currajong with a K, and it came up with Currajong North, that would be 1.5. It would be 1 for the Levenstein distance plus that 0.5 penalty. And in the end, what I did is I took the list that I'd saved, which had within my threshold of 2 or so on, or 2.5, and I sorted it and I printed it out in order. So that gave me, for the word Currajong, the first 20 results I was pretty happy with, starting Currajong with a C, which is what we'd expect, going to Currajong with a K, and then things like Currawong Beach, Currajong Corner, Currajong North, and so on. So those are all the things that fell under what I was looking for. But the other day I came across a really nice algorithm, so I thought I'll just share this one as a special surprise. So I don't know if you must have come across certain search things, like if you use Vim and you use Control-P, fuzzy searches, where you type something like RRJNG, and it comes up with Currajong. Somehow magically, if those letters appear in order, it will find it. So I've come across this article, and somebody had implemented a fuzzy search in Python. And I'd never thought about how you do it, but the method was ridiculously simple. You take what the user has typed in, and you convert it to a regular expression with dot stars between each letter. And then you search for that regular expression. And we can implement that in code really easily. What we've done is this fuzzy finder takes the code that the person has typed in. It uses dot star dot join, whatever they've typed in. In other words, between each letter, it will do a dot star. And it just uses Python standard regex. So using RRJNG, the last line, inside this data, we get Currajong. If I type C, RRJNG, we wouldn't have found Currajong with a K. But I've been thinking about ways to get past that limitation. What amazed me about this is that it's actually ridiculously fast, which I never expected. 0.085. So this is, in fact, turns out to be the fastest algorithm of them all, which surprised me because regular expressions can be incredibly slow. So finally, what do we conclude? Well, I've said there's no single best algorithm. You can't say, I want to do fuzzy searches, what's the best algorithm? It depends on your data. It depends on what you consider false positives, false negatives. etc. Second one is that for each algorithm, there's a trade-off between accuracy and speed, as well as other things. So some are more accurate. A good way is actually you may find a hybrid of two algorithms. Use one algorithm that gives you a wide range. Let's say you've got 1 million names. You may use something like Soundex to narrow that range down to 1,000 or 100, and then use Levenstein on that smaller set. So always there's a trade-off. And then understanding how the algorithm works allows you to improve the algorithm. And I've added this, that when I actually went back to the Gazetteer about a week ago, I noticed that it was doing fuzzy searches, or maybe a month ago. And then I went back today, and it didn't seem to be doing it again. So I don't know what's happened there. Anyway, how does our story end? Well, it ended with me updating my algorithm. So I've now got, let's say, Currajong. And I should get the results back a little bit faster, depending on our internet. OK. And so now we can zoom in on this area, because we want a happy ending. And let's just zoom. We're playing CSI or one of those things. We'll zoom. Zoom. Ah, there's a little spot there. So let's just zoom a bit more. And we found the red car. Thanks very much.
Thank you very much, Martin, for a very entertaining talk. And here's a gift from the organisers.
Thank you.
Do we have any questions for Martin? Up here.
Yeah, I was just wondering, with the Hamming distance, did you think about differentiating between a Hamming distance that would be like C and K versus C and M? Because they just have C and K similar sounds. So it seems like C and M should be a 1, but maybe C and K should be a 0.5 or something like that. Is that a consideration?
OK, a simple answer is no, I didn't consider that. One of the things that Levenstein actually does offer is to give penalties to whether you're inserting, deleting, or substitution. And in the end, you remember when we were looking at that fuzzy search, one of the things I thought about is that where we had a C, let's say, we could replace it with a character class, CK. So it would do a fuzzy search on the character class CK star RR star NG. Thanks.
Any other questions?
I wanted to refer back to your comment about using different algorithms in tiers, so you'll have filters along the way. I think it'll really depend on what your definition of a false positive or negative is, but have you found, like, is there consistently a tier that, or a set of hybrid methods in a particular order that really works well consistently? Thanks.
Right. I haven't tried any, but I guess there are two broad classes of algorithms, and the one is the ones that you can pre-index, like Soundex, Metaphone, etc. And so I think, particularly if you've got something in a database, so you could index on Metaphone, or there's actually an advancement on Metaphone, that could work well as the first step in getting relevant or possibles out of the database, and then using the Python algorithm, whichever one it is, to filter that list the second time. But that's all I've really considered there.
Thanks for the talk. I've had good experience using a Python fuzzy matching library called Fuzzy Wuzzy. I don't know if you came across that in your travels. It is an implementation of Levenstein distance, and one of the neat things it does is automatically out of the box gives you like multi-token matching. So for Currajong North, it would do a separate test for both tokens, Currajong and North, and then if it found a match for obviously one of them, then the whole longer token would be a match. So that's sort of how it gets around that problem that you alluded to. So I guess that's possibly more of a comment, but it's a good library for reference, yeah.
Yeah, thanks. I wasn't aware of Fuzzy Wuzzy.
Any more
There's one
questions?
down here, front row.
Hi. So Jellyfish clearly works on English, but have you tried like using it on other languages?
Right.
Yeah.
Okay, so that depends on the algorithm. So, for example, Metaphone and Soundex are clearly English because they'll say, okay, a C and a K is a similar sound, a B after an M. But when we get to things like Levenstein, it really works only on the characters, independent of what they sound like. However, I think, yeah, so in certain languages, we may have things that have a longer distance, but I think that, from my experience, the Levenstein works pretty well across languages because it doesn't care what the character represents or what sound. It's only looking how many differences there are.
Any more? If not, please. Claire.
So I work in bioinformatics, and we do a lot of string matching, but it's not English strings; it's DNA strings, and it's similar algorithms. And one of the algorithms that gets used a lot is kind of an extension of Levenstein. So Levenstein, but with different scores for different characters, as someone was just suggesting, and different scores for short gaps as opposed to long gaps. I just wondered, do you know if that sort of thing gets used in English string matching, or are those algorithms available to you? Are they useful?
Okay. The simple answer is, as far as I'm aware, not. However, there's one more algorithm that I didn't discuss, which is Jera-Winkler. And things like spell checkers, a very common mistake also in things like SNPs and that, is the transposition of two letters. When people are typing, they'll often type friend, F-R-E-I-N-D. So Jera-Winkler will count that as a transposition as one, and a insertion, deletion, etc. as one as well. So that's the only one I'm aware of. I think, obviously, in bioinformatics, there's a lot more value in looking for those sums.
The strings are very long.
Yeah, yeah.
Yeah. So we have some different algorithmic
Things like
constraints.
blowsum and PAM and yeah.
Last one.
So you mentioned Soundex and Metaphone as indexable phonetic structures. Do you know of any others?
I think there's one called Metaphone 2. And I do believe that there's another one. I can't think of it offhand. If you just, either Google or go to Wikipedia Metaphone, I think they'll mention the other one, which I can't think of now offhand.
All right, fantastic. Let's thank Martin again.